inviting me, and also it's always great to come back to visit here. So I will talk about some variable selection problem. This problem has been going on for quite a while. May not be what Bayesian really like. So I've been a good friend with Don Rubin for many years. He always was against variable selections because, as people know, you probably can put a full model averaging everything and so on. But I think in many scientific problems, variable selection is still of practical use and also of scientific interest, because you don't really want to use 10,000 genes to predict whatever health status. You want to be more precise and more interpretable. So this part, the first part, is pretty much well-known Bayesian linear regression, and I'm just formulating them in a sequential Monte Carlo way. So this is actually an interesting topic. I have been searching to see who have done some of this sequential Monte Carlo particle filter for variable selections. I did find a couple of papers, but none of them are cited much. So it seems people either are not interested in this or don't know how to do it in the correct way, or don't find this to be very useful. So I think if you want to be more parallelizable or generalizing to big data, so to speak, sequential Monte Carlo seems to be a good way to go, as Steve just mentioned. The question then is, for variable selection, how we do that. For linear ones, so that's why I started to be interested in stepwise methods in the past few years, and which then lead me more away from Bayesian formulations, more from non-Bayesian perspective. But I still notice that the Bayesian criterion seems to be still a better criterion than anything we have been using in the literature, like Lasso and so on. And in most of cases, we simulated or we analyzed in some real data. Lasso seems to give a reasonable answer, but not the best you want. For linear regression models with conjugate priors and so on, you can actually turn the variable selection problem into this sampling from that distribution, which may or may not be doable for some other. Does this work? Probably not. For other type of generalized linear models. But for linear model, the nice thing about having this closed form distribution by integrating out the continuous variable beta is quite handy, very convenient. You can literally just optimize this discrete function, although this discrete function can be hard to optimize. So there are, and of course, if you want to use some approximate criterion or some other criterions, you can just plug in that HR as a criterion function. There's some proof showing that if you take tau equals to 2 and use this Mallows CP criterion, this is approximate Bayesian under some prior settings. And there's different criterion you can put into that, and you can just implement the true Bayesian by doing some integrations for all this data. Now the question is, so how do we optimize this? So we can do stepwise. So the classic stepwise methods is quite applicable here. If you go to R package, you use the function step or stepwise. That's essentially doing this, and you can input a criterion like AIC or BIC, which is just optimizing. So which is the edge function I'm using here. It could be AIC or BIC and so on. And you can choose some other things you want. But if you also want to do model averaging, what can we do? So model averaging actually does have some use, some advantages, especially in very weak signal case. In which case the lasso actually fails. If you really think about very, very low signal, like 1% signal, that's R squared, which is typically a lot of financial data, then lasso typically fails because just throw away variables in whatever optimal way is bad, because the price to pay to throw away bad ones is pretty high. But Bayesian averaging actually can do a reasonable job in that case. So that's the only case I find to be able to beat the naive linear regression. So it's kind of funny. So if we don't want to do full MCMC, so what choices do we have? So there's a earlier approach we explored. We tried to explore the sequential Monte Carlo approach for this, but somehow was tracked into this framework. It's trying to do sequentially, but eventually we did it a few loops. So if you do a one loop, it's probably just sequential, but we find it's probably not as good. One simple thing is so-called iterative conditional maximization, which is you conditional on all the selections of other predictors, and you try to say whether I should set this predictor to be one or to be in the model or out of the model, which is very easy. This delta thing is a little forward-looking, which we call. That is, we don't just optimize by changing one variable, fixing all the others, but we give a window of delta so that we average over all possibilities in the next delta variables and then optimize this. Of course, if your computation power is high enough, you average everything that you find optimal. That's even better. And this is something. This is iterative conditional sampling is also trying to do same thing, which is, but instead of optimizing, you sample whether this variable should be in or out of the model. So these two approaches, and also we explore something even more complex than this with what we call piloting, which is for the other variables, for this approach, we fix it as 0, that is not in the model. But you could sort of do a little bit perturbation in the future or piloting in the future, trying to get a better estimate of whether how likely this current variable should contribute to the model. So these are some of the simulation results. I compare with the naive forward-backward approach, how many false positives and the negatives and so on. So this iterative method seems to be reasonably well, just pretty slow, even for this many variables. But if you have multiple cores, you probably do better. So the stepwise approaches just allow you to do one step, so which is a little more restrictive, but probably more time efficient. And for this approach, for this particular problem, you could do the typical stepwise approach. Typical stepwise approach is you pick one variable which is you consider as the best to add, and then you take another one which is the best second one, and so on. That could be expensive because each time you consider all the variables. Another way you could do is to just line up variables each time you add just one variable and don't consider all the others, but just consider whether this is good or bad and put it in, and then you get in another. But of course, the problem would be you may have correlated variables, and once this get in, you may prevent some other more or better variables to get in. So that's the serious problem here. So there are some proposals. So here is more speculative than having the results. One is ordering, how you order the variables. You could compute some pairwise correlations among the axes and put the more correlated variables together. Let's order them. And also using the sequential Monte Carlo framework, you don't have to sample this 0 and 1, that is, put that particular variable in or out of models according to its current value. You could be more lenient by giving them the earlier variables sort of more flexibilities, closer to 1/2 to be in and out of models. By using multiple particles, you might be able to explore the possibilities, all the possibilities. So, but in any case, so if you follow the standard sequential Monte Carlo recipe, that is, you do conditional probabilities for whether you should put next variable in and out, then the probability can be computed in this way. Then you can define the weight accordingly. So then you can recursively update the weights, and because each step you only consider one variable to be in and out, and this optimal resampling methods by Fernhand and Clifford can be used here to make resampling much more efficient. So also I think one particular aspect of particle filter which I dislike is particle makes you always feel you are resampling every step, which is not necessary. If you do it, which make the issue Steve mentioned is especially severe, which is communications, because you resampling, you have to communicate. But if you resample every many steps, like 100 steps or so on, then you probably can avoid some of that. So another possible way of doing SMC in this variable selection is following the classic stepwise regression approach, which is at each step you consider adding in one variables with probability proportional to how good it is after adding that, so which is PV. And of course, V could be empty, 0, which is you don't add anything. So then you can do this type of sampling. The problem is now you have to consider all the P variables each step. So you can still keep like multiple particles, and some of the particles, I think for efficiency, you could combine some of the particles to make the computation evaluation more efficient. You don't have to reevaluate this function for all the particles. So the weighting part should be similar to the previous one. So these are all speculations. We thought this is doable, just whether this is efficient or whether this can be better, it's not clear. So intuitively, I think this can be better when you have large data and also large P, better than the vanilla MCMC, which is typically very hard to move, to converge fast. So this is about the linear part. So recently we have been studying this nonlinear questions for a while. It's actually very interesting. There's some neat connection with the Bayesian formulation as well. It didn't occur to us at the beginning, and also related to the discretized say classification problem, which will tie into this afternoon's talk. Okay, so I don't know how many of you are familiar with this multiple index models. This is, I think, one of the sort of the most or the simplest or most approachable nonlinear models beyond for high dimensions. So this is just saying that my response variable is only related to x in some linear directions. Here is d. So x dimension is still p. P can be 1,000, but d can be 2 or 3. So that's the dimension reduction. So there's also variable selection aspects of this problem. That is, the betas can be a sparse vector. That is, beta can probably only dependent on a few x's, which will be more interesting in this case. So this model was proposed by Ke-Qiao Li in 1991 as a dimension reduction problem. In his time, like 20 is big data, right? 20 dimension is big. So typically P is 20, but D is 2. But if you look at this model, even when D equals to 1, it's more general than the linear regression model. Linear regression is a special case for this. F is allowed to be an unknown link function. In his original framework, it has to be like monotone, smooth, but later we don't really have to have that. But theoretical properties becoming murkier if you remove the restrictions. So the betas should not be identifiable because if you multiply a constant and divide by constant, these things still hold. But the space spanned by this beta is identifiable, and the variable selection is identifiable. So there's two aspects of identifiable part. One is which variables are actually contributing to y, and also what is the subspace spanned by this beta function. So the slice inverse regression proposed by Ke-Chiao Li is very interesting methods. But now I think it's easier to illustrate you through a graph than this formula. So suppose this is my cartoon framework. Suppose this is x is 2 dimensions. I can't draw anything more than 2 dimensions here. So these are x's, x1 and x2. Suppose y dependent on x1 and x2 only through x1 plus x2, right? So suppose these are the y, which is dependent on these x points plus a little noise. So that's the truth. But of course, you don't see these red points. You don't know that's the relationship. So you only know this the observations, which is y corresponding to each pair of x1 and x2. The question is, can you find this reduced subspace, which is x1 plus x2, that actually is underlying the functions of y? The idea is quite simple. It's just discretize y, so he call it slicing, and then calculate the corresponding x's for those y's, calculating their sample mean, so they summarize into a point. And then the second slice, which is the blue one, and also you calculate all these points. And third slice, and fourth slice, fifth slice. So now you have 5 slices, and you have 5 sample means. It turns out they actually lie on that space subspace very well. So there's theory to prove they, of course here I sample x1, x2 is the standard Gaussian. If they have correlation, then they have to be adjusted by covariance matrix. So in that formula, if you can see that, so that's the final thing you see. So if it's adjusted by the covariance matrix of x, this gives you an estimate of that subspace. And the interesting thing is that this actually discretizes y, and then try to find this space. And in this particular case, actually, if you cut y just by half, you can get this line. And this line is the thing everyone should be familiar with. That's LDA line, the linear discriminant analysis. So that's actually exactly the same as LDA in that if you have the corresponding the cuts. But if you have more than 2 cuts, then it's a little different, but it's very close. So this is the connection with that LDA things I'm talking about. So there was literature about more formal models. This is not the real model. This is more like a working model. So if you assume this model, then the solution of this subspace, the maximum likely estimate of this subspace is the same as the estimate we just proposed. That's the slice inverse regression estimate. So more precisely, if you assume that the every slice conditioning on condition on every slice, the x's have a distribution which is Gaussian with a mean dependent on the slice, and also the same covariance matrix, which is exactly the assumption behind LDA. And also, this is more for variable selections, ignore this part. Then if you assume that mu s falls into some low-dimensional space, like a line, where you assume you know D or 2-dimensional space, then you can try to find the maximum likely estimate of the span of the subspace. That will coincide with exactly the solution I just described. So you can see that if you make a D equals to exactly 2, you can have an LDA solution of this. And based on this formulation, this is actually starting to connect with the base. So you can actually treat it as a true to model, then this is more like a discretized y, conditioning on y, the distribution of x will be multivariate normal. Then you can actually have a Bayesian version of that and Bayesian variable selection for this. But you can do it stepwise by using the likelihood ratio or Bayes factor analysis. But each time you consider adding new variables and to see whether use that kind of multivariate normal relationship, you can calculate this Bayes factors quite easily. So we did that. And also, there's a very simple generalization which turns out to be quite surprising for us. It's quite useful. That is, if you assume all these different clusters, different slice axes, have different covariance matrices, then the previous framework of dimension reduction is no longer does no longer hold. But this gives us a more flexible algorithm which allow us to do a quadratic discriminant analysis. Right? Linear discriminant analysis assume each data cloud have the same covariance matrix. Here, if you assume they have different covariance matrix, you can actually do a quadratic discriminant analysis. And more interestingly, if you take that framework, all the Bayes factors are easier to compute because you don't constrain. Each slice have the same covariance matrix. They each can have their independent Bayes factors. So here we propose, based on this formulation, we can do stepwise regressions based on the different normal distributions. And it turns out the test statistics we need to use is very simple to interpret. That is, if you conditioning on the current selection of variables C, and you say whether the variable J should be useful or not, and the criterion considered is the sigma J square, which is the variable xj regressed on the current selection of variables C. So that's the residual sum of squares. And here, sigma J h hat is just the residual sum of squares after regressing this variable J with other variable within each slice. So that's the difference. This is the difference of these things. So intuitively, if you think about the new variables, and if the relationship of new variables and your current selection of variables is not affected by the changing of y, then it means they're conditionally independent, right? Because the relationship of these new variables and your current selection x is not changing as you're changing y, so as you're cutting slices. But if they are related, that means this relationship is changing as you're moving through the slice. So that's the intuition. So it turns out to be quite useful. So this is the very simple illustration. Suppose we simulated this. And first of all, it's hard to do screening by linear regression, but you can do first do variable selection by slicing. That is, if you slice y, then you can look at each variables and see how their distributions changes at different slices. In this particular case, you can see the variances of x's within each slice are different. So this is the first criterion we can use to select the first variable. And then once you select the first variable, in this case x1, then we can consider selecting second variable, pretending that we haven't found the second variable yet. Then this actually gives you so the simple illustration. So you can see that conditioning on the slice, the tallest slice of y, which is colored red, you can see the do linear regression of x2 on x1. So this is the marginal regression of x2 on x1. There's nothing because I simulated the standard Gaussian. They have zero correlations. But if you do this, you can see the slope, right? They're quite sharp, although it's not normal. So this is the second slice. You can see the slope is changing, the third slice, and the fourth, fifth, and so on. So you put them together, you can see at different slices, this relationship between x2 and x1 is changing. So this gives you a very strong statistic to detect them. And so, of course, since this is the Gaussian case, you can we did make it Bayesian, but in a stepwise way. But we can do it more stochastically in the sampling way. This is still optimization. So this is just algorithmic details. I wouldn't. And there's a further extension of this, which could be interesting, but it's actually computationally a little tricky. We experimented a little bit on this. One thing is we cutting Y seems to be unnatural model, right? So one potentially or standard approach for Bayesian statisticians is to introduce some latent variables. So suppose we have a latent type of each individuals, then we can say my X is predicting T, and or conditioning on this latent type, Y and X are independent. So this is one model, which may or may not be desirable. But this latent type models are interesting. That is, if you have so this we first thought about this in genetics, which are more or less real. That is, if you have individual type, then all these features are similar. So like height, if you have same type, some genetic types, then your height have variations, but very similar. So that group of people, and also their genetic background should be similar in some sense. So then we can model them separately. But this is not exactly regression yet. This is more like inverse models. We really want to handle some non-symmetric rows of Y and X, so which we will come back later. Okay, so here I jump to LDA and the QDAs by trying to explore this series type of approach further. Because the series model is assuming the conditional independence, conditional Gaussian models, which is conditioning on each slice, the axis have Gaussian distribution, and use that to do further like dimension reduction and variable selections. And here, if we think about them purely as discretizing Y, and then do a linear discriminant analysis or quadratic discriminant analysis, we get very similar answers, and we can come up with this formulation. We can also do variable selection. There are quite a few papers on variable selections on LDA and QDAs. But problems with this LDA-QDA approach, many people probably know, is that they are not very robust. If you have non-normal case, they are very unrobust. Also, for quadratic discriminant analysis, it's a little tricky because computations can be difficult. But anyway, there are two existing ones. We all have compared a bit. And one simple way to make it more robust is to turn to logistic regression instead of using the conditional on Y on the X distributions. We inverse that. We directly model the predicted distribution of Y given X. This is well known in statistics. For linear case, for LDA, you have just a logistic regression with only linear terms. But for QDA type, you will have this second order terms. So in general, we can consider logistic regression with second order terms. But when P is reasonably large, like 1,000, all the interaction terms, if you even for Lasso type of things, it's hard to cope with. Like that will be 500,000. So we recently proposed a stepwise algorithm for quadratic logistic regression. We call it SODA. SODA is, I just described the algorithm here. It will initialize with nothing, and then you add one, you take one variable at a time. So when you take one variable in, you consider all the quadratic terms it has, and also it has with other existing predictors you selected. In other words, you don't break the individual terms of these variables in consideration. You consider everything. So then this is sort of linear type of consideration. So this is an illustration. So for example, backward is to remove terms. Backward you can remove terms individually. So for example, this is an illustration. The first step is just add variables. So x1 is added in. This is notation for the square terms. This is notation for the single term. And then after that, we add x3. But when you add x3, it's all the quadratic, all the second order terms are considered. Then we add x2. And then by after adding x2, if the signal is strong enough, you say there's nothing else to add. Then we can do the backward eliminations. Each time we can eliminate a term like x2 squared or x1, x3. So this gives us a flexibility of being quite fast. I think forward step is linear, and the backward step is, if you assume the sparsity, backward step is also less than linear. So this algorithm, another aspect of this algorithm is the criterion we use is the Bayesian criterion called the extended BIC, proposed by someone, which consider both the number of high dimensions and also the data size. So this is a simple comparison with Lasso logistic regression. For Lasso logistic regression to work, there's a quite strong criteria, quite strong condition to say it's called the incoherence condition. That is, the variable, the predictors cannot be too correlated. If they are too correlated, then you don't have the consistent solution. So this is one case where the coherence condition holds. There's another case which we actually got from microarray data. The incoherence condition does not hold. And we just simulated some more data using the same covariance structures from that microarray data and trying to do this analysis. So you can see for first case, the two methods compare quite well. There's very little differences for false positive, false negative in variable selections. But second example, you can see the SODA perform much better than the logistic Lasso. And so this is the false positive, false negative is getting down. So and we have a few more examples. I wouldn't tell too much about this. In general, the SODA approach seems to work quite well compared to the existing quadratic or linear discriminant analysis variable selections. So if you compare with, these are some of the existing approach, and the black is SODA, and the yellow one is the Oracle, which we know which variables we should use. For the runtime, the stepwise is definitely much better than some. And even these few approaches were supposed to be developed for large, high dimension, large data, because they use some kind of like first approach use some kind of screening, then add more variables. But because they have to compute inverse of estimated covariance matrix along the way, so it's very expensive. So here is an example of Michigan lung cancer data, which has two classes, and I won't give you details. So all the big people have analyzed this at the Efrons and Tiptronics, and we are better than them. So it's pretty much the result. So you can see that even like you look at the result, we can have cross-validation error only 0.11, but with 2 single terms and 2 interaction terms, and the EBIC is 69.8. So if you look at the logistic lasso, it's not close to that. But anyway, so last few minutes, let's go back to the continuous response case. So we call it the S-SODA. So SODA is only for logistic regressions. So we want to make connection back to the nonlinear problems, the slicing ideas. So if we do the slicing as the third slice inverse regression model type of approach, our previous work were based on, as I mentioned, more methods more like LDA. But if we do the logistic regression aspect for that part, can we gain something? That's what we want to see. So in this case, we just say if we slice the y and we just apply this lasso to the slice variables. So let's see how it works. So one thing we notice is all the relationship of y and x is not necessarily quadratic. It can be anything. So the fact that using logistic regression with only quadratic terms does not limit the continuous relationship between x and y. But what type of relationship can be and which type of relationship cannot be captured by those things is not mathematically well understood, but I would suspect that I think any relationship, if you cut the slice large enough, this model can approximate well. So we simulated all the cases with different dependencies among the x's and also non-normalities and so on, and then compare with many methods like lassos and so on. For linear model, the first example is for linear models. Lasso is doing pretty well, and SODA is actually doing okay. I guess for later variables, you can see SODA and this N series is doing quite well. The N series, we call it normalized series. That is, you sort of use rank data instead of original data to avoid some kind of issues with Gaussian problem. So overall, the simulation is quite reasonable. This is the worst example, but still can work in some cases. We can also do the model fitting by SODA, but it's a nonlinear models. Like in this case, the left side is the real continuous function. The right-hand side is the fitted by this SODA methods. This is another real data which is fitted by this. But if you do linear regressions, you can get that. Okay, so the final speculation is we really want to make this a Bayesian version. We haven't. How we can make it more formally Bayesian? So of course, this latent variable should be used, I think. So we can do a latent indicator variables, which we can use a Dirichlet process prior to model it first. So that's how many clusters of this y's. And then we can use a predictive model on j's by using logistic regression models. But then we need a good Bayesian algorithm for doing Bayesian logistic regression models. The one we explored is this polygamma process methods proposed by Nick Paulson's group. But I also noticed this afternoon's talk, I don't know whether it's still going on or not because I haven't seen Tamara yet. It's on exactly this topic, which I will be quite interested in knowing. And another theory that's actually make the last line difficult is in the previous linear case, we can get the marginal distribution of the variable selection, the indicator variables. But for logistic regression, at least I don't know how to do that. So in that case, how we do this sequential things, it's unclear. We could do a brute force one by particle everything. So every variables in your model, like including continual variables, can be represented by huge particles. But that could be very inefficient. In any case, I will just, we did some exploration, just say, initial study seems to be reasonable. There are some references related to this talk. Then many of my former students have been involved. Thank you very much.
So how, I saw you had an example where P was 1,000. How much have you pushed these methods in the simulation?
We probably furthest one we pushed was like 2,000 or 3,000 P. Yeah.
Okay.
Yeah. Oh, by the way, this always actually put on the web. I think it's in this R repository. So if you're interested, you can explore this soda. It's quite reasonably written.
Okay, so I think people are thinking about lunch. So if we can just thank the speakers from this session again.